Good morning or good afternoon. My name is Ashley Gildelamadrid, and I chose to do my final paper and presentation on a review of high-volume fly ash mixtures offering a sustainable solution for concrete production. What I reviewed along the way was high-volume fly ash as a sustainable solution for concrete production because the addition of fly ash in concrete mixtures reduces environmental impact of concrete production. The addition of fly ash in concrete mixtures lowers costs. The addition of fly ash in concrete mixtures has the ability to improve concrete properties in fresh and hardened concrete. I have 3 examples from journal articles to support the improvement in concrete properties with fly ash added as a replacement to cement. The addition of fly ash in concrete mixtures also reduces landfill waste. High-volume fly ash mixtures reduce environmental impact of concrete production by, the environmental impact of concrete production that is reduced with the use of fly ash has to do with the cement replacement in the concrete mixture. Fulfilling the LEED and ASTM standards. LEED stands for Leadership in Energy and Environmental Design. ASTM stands for American Society for Testing and Materials. Just as a reminder. Fly ash, in regards to environmental regulations and building codes for LEED and ASTM standards, meets these standards when used as a replacement for cement and concrete. So, the use of supplementary cementitious materials, or SCMs, such as fly ash, as a replacement for cement and cement mixtures is an effective way to be sustainable in the construction industry. SCMs have pozzolanic activity, and this can help to improve later properties of concrete. Fly ash is a byproduct of industrial production. SCMs are sustainable in the construction industry because they can reduce greenhouse gas emissions and they can recycle resources. Using a geopolymer binder, such as fly ash, can significantly reduce the global carbon dioxide emissions and energy consumption, making it much more sustainable than Portland cement. The environmental footprint and greenhouse gas emissions of the concrete producers can be reduced when fly ash is used as a cement replacement. Using fly ash as a replacement for cement and concrete mixtures is a way to also recycle resources, which reduces the need to extract new raw materials from the earth and the recycling of fly ash, minimizing landfill waste. It also lowers costs. The use of fly ash in concrete mixtures lowers costs because, fly ash is a lower cost material compared to cement because cement is one of the most expensive ingredients in a concrete mixture. High-volume fly ash lowers costs in concrete mixtures because it reduces the amount of cement needed in the concrete mixture. Fly ash is a cheaper and popular substitute for cement. So, by replacing cement with a certain percentage of fly ash, it's beneficial to keeping costs lower. The location and availability of fly ash has an impact on costs. It does depend on where the fly ash is located, how available it is, and other factors that affect the construction industry market on the price point of fly ash in a concrete mixture. If there is an increased demand for fly ash, the supply and prices can fluctuate as well. Contacting local suppliers and ready-mix plants can be a good place to start to discuss needs, availability, and pricing of fly ash. Fly ash has less long-term maintenance than Portland cement. The concrete produced from geopolymer binders like fly ash is sustainable and can have unparalleled engineering properties. This contributes to the improvement of development and sustainability in construction practices. So because of this, fly ash has the benefits of unparalleled engineering properties such as improved workability, durability, and resistance to certain chemical attacks. Fly ash has less long-term maintenance than regular Portland cement does. This helps to lower the cost of fly ash throughout the lifetime of the concrete the fly ash was mixed into. If the concrete mixture that contains fly ash can earn LEED points, then potentially even more cost savings because of green building projects can be an outcome. LEED points can be earned through fly ash when it is used as a replacement for Portland cement. The LEED points can come from a project that uses fly ash as recycled content and potentially innovative techniques. The improvement of concrete properties. High-volume fly ash can change and improve concrete's properties when used in a concrete mixture. Examples of changing and improving the concrete's properties are the workability of the fresh concrete that can be enhanced, the later age strength of the concrete can exhibit increased strength compared to conventional concrete. The durability can be improved. the permeability can be reduced, and this improves the resistance to water penetration in the concrete. The setting time of concrete is delayed when using fly ash, and this can be a beneficial application. Drying shrinkage and cracking can be reduced, and the harmful effects of alkali-silica reaction can be mitigated with the use of fly ash. Workability is improved when fly ash is used as a replacement in concrete mixtures because of the spherical particles that reduce friction and require less water. Durability is improved primarily because the permeability is reduced and the durability is enhanced by its resistance to chemical attacks. Permeability is improved because of the number and size of interconnected pores in the concrete matrix. Later age strength is improved through a pozzolanic reaction. This pozzolanic reaction will continue over the life of the concrete, and this makes the concrete matrix denser and increases its strength and durability at later ages compared to Portland cement with no supplementary cementitious materials included. The setting time of concrete being delayed when using fly ash is because of a reduced heat of hydration. This can be a beneficial application because a delayed setting time can prevent thermal cracking when using fly ash in a larger concrete structure. Drying shrinkage and cracking are improved and can be reduced when using fly ash because the amount of cement paste is reduced, which reduces its shrinkage potential, and the microstructure of the concrete is modified when adding fly ash. Fly ash improves and mitigates chemical reactions in concrete. Alkali-silica reaction and sulfate attack are some examples of chemical reactions that are mitigated with the use of fly ash. The pozzolanic properties of fly ash are enhanced when there is a reaction with calcium hydroxide in the presence of water to form cementitious compounds. Fly ash contains silica and alumina. The silica and alumina then react with calcium hydroxide and produce additional cementitious compounds such as calcium silicate hydrate, CSH gel. Results of using fly ash were that workability was improved in mechanical strength when there was up to 50% replacement of fly ash in a self-compacting geopolymer concrete binder. Fly ash, because of its pozzolanic properties, contribute to improved flow characteristics and a dense microstructure in the ultra-high Portland cement. When replacing cement with fly ash in UHPC, a range of 20 to 30% is ideal for replacement. The carbon footprint for UHPC is reduced when replacing cement with fly ash. Strength over time will be increased in UHPC with increased fly ash dosages. When looking at the compressive strengths, the inclusion of 5 to 10% fly ash mixed with the effective microorganism solution significantly increased the strength with curing age. 10% displayed the highest compressive strength for the bioconcrete prepared. So our first example is an example from the article Enhanced Maturity Modeling for Sustainable Concrete Mixtures Using High Volume Fly Ash. And it focuses on the 14-day and the 28-day models when looking at a concrete mixture, and it focuses on type F fly ash primarily. So it is observed concrete mixtures in 14-day maturity models with 35% of type F fly ash, 50% of type F fly ash, and 35% of type C fly ash. There were 3 approaches taken to calculate activation energy and prediction models made on these approaches. The first approach, the limiting strength of each mixture at different curing temperatures, was considered. The second approach, the setting time of each mixture, was considered. The third approach, the limiting strength was kept constant for each mixture regardless of curing temperatures. The compressive strength of these concrete mixtures in the 14-day maturity models for fly ash type F show improvement in estimating the in-place compressive strength. The setting time approach showed encouraging result and showed that this approach could be used for developing prediction models. The 14-day data consistently provides lower errors of prediction errors than the 28-day models for high-volume fly ash concrete mixtures. Strength development rate in concrete slows down from the 14th to the 28th day, so 14-day data could provide more accurate strength predictions. This can lead to less testing. A 14-day new maturity strength prediction was examined against the traditional maturity modeling suggested by ASTM C1074. The 14-day pull-out force versus compressive strength showed small improvements for the 35% of type F fly ash and the 50% of type F fly ash mixtures. The mixture with 35% of type C fly ash had better estimates with the 28-day correlations. The 35% of type C fly ash also show us that the 14-day maturity models underpredict the in-place compressive strength. The 35% of type F fly ash and the 50% of type F fly ash using the 14-day maturity model predict higher values of in-place compressive strength. The mixtures with 35% and 50% of type F fly ash have more accurate estimates of in-place strength for the 14-day maturity models than the pull-out correlations. A second example comes from the journal article Experimental and Informational Modeling Study of Sustainable Self-Compacting Geopolymer Concrete. The fly ash percentage in the concrete mixture is the biggest result from this study of what's important here. Results of the testing for fly ash replacement showed that fly ash is very beneficial for self-compacting concretes with binders with low fly ash levels. The workability was improved when the fly ash percentages were at 40% to 50% because of the shape of the fly ash particles. When the percentages of fly ash replacement got higher, the workability of the mixture was reduced because of the high water absorption and poor structure of the fly ash particles. When the fly ash replacement levels for GBFS were 40, 50, and 60%, the flowability, resistance to segregation, ability of filling, and passing capacity were on par with the standard requirements for fresh concrete characteristics. The plastic viscosities of these mixtures reduced between 0 to 50%, but increased when fly ash was at 60 to 70%. The chemical compositions and the changes in the physical properties of these mixtures would be why there was an increase in plastic viscosities when fly ash was increased in the mixture. At room temperature, fly ash had a slower setting time than other binders. When there was a high volume of fly ash in the concrete specimens, the specimens displayed distributed cracks with a brittle failure. The fly ash percentage mix of 30% revealed fewer microcracks, micropores, and non-reactive particle than the mixtures with 50 or 70%. The mixtures with more than 30% fly ash had a lower compressive strength. And the last example comes from a journal article, Crack Healing and Rheological Properties of High Content Fly Ash, Slag, Silica Fume, Green, and Sustainable Cement-Based Materials Incorporating Crystalline Admixture and Calcium Alginate Biomass Hydrogel. And this focuses on self-healing ability that comes with the crack healing and sustainable cement-based materials, and the mechanical properties, how strength with fly ash is actually stronger than with Portland cement, for example. Weight percentage of fly ash used in the mixed proportion was 30% in this test. The tests that were observed focused on the mixture proportion specimens and cracks that developed in the cement. Water permeability amounts, crack measurement / width was taken, mechanical properties, and crack healing for self-healing performance of cement concrete. The cylindrical specimen was then split to further observe the crack that developed and healed. Looking at the rheological properties, when fly ash partially replaced cement, the shear stress of fresh paste decreased. There were calcium alginate beads in the paste, and the calcium alginate beads with the fly ash played a bearing role in the shear process, thus reducing it. The hysteresis loop area, which represented destruction of fluid structure caused by shear process with fly ash, decreased. Fly ash significantly reduced the yield stress and plastic viscosity of the paste. This had to do with the shape of the fly ash. It was a large spherical particle and had low reactivity. When it was undergoing the shear process, fly ash was playing a bearing role to reduce friction between particles. The mechanical strength of mortar for the mixture was increased, and the addition of SCMs had the ability to improve the permeability of mortar. Fly ash was observed to have the ability to enhance the self-healing ability of cement mortar. So landfill waste was also reduced through all the review of this. With fly ash being a byproduct of coal combustion, it can be repurposed in various applications. The applications are concrete, road construction, and soil stabilization. These applications reduce the need for virgin materials and reduces the waste that is also sent to landfills. Landfill waste being reduced is a long-term reason why high-volume fly ash is a sustainable solution to Portland cement. Fly ash is a big contributor to landfill volume and potential environmental issues that could arise from the fly ash being stored at the landfill. When replacing cement with fly ash, the demand for virgin materials reduces and the amount of waste sent to landfill significantly decreases. An environmentally responsible society must develop low-carbon infrastructure through optimum use of cement and proper use of fly ash, a waste byproduct that can significantly pollute nearby water resources, the air, and soils otherwise. Rather than being disposed of, fly ash can be useful both environmentally and economically if it is used in concrete. So, by this replacement, environmental concerns about disposal are addressed for fly ash. We can think of the replacement of 1 ton of fly ash in a mixture means that 1 ton of cement will be displaced, and the amount of waste going to a landfill is reduced because of the fly ash being used. So conclusions of this review: the reviewing of high volume fly ash as a sustainable alternative to cement used in concrete mixtures shows that fly ash is indeed more sustainable option to use in a concrete mixture than Portland cement. Ultimately, replacing cement with fly ash to a certain percentage in the concrete mixture will offer both environmental and performance benefits for producing and using concrete. The fly ash usage has to be optimized to ensure that the fly ash is being used to its full potential and benefits it can provide to the mixture. It reduces the environmental impact of concrete production, lowers costs, concrete's properties can be improved with the use of fly ash, and landfill waste is reduced, thus making fly ash a great replacement for cement if one wants to have a sustainable concrete with high strength and durability. Thank you, and have a great rest of your day.